Hello, everyone. Good morning. Happy Monday. So I want to use this video to introduce you our new lecture. It's about temperature and energy in our atmosphere. In the past weeks, we have many very violent weather events in Texas. We have that very serious winter storm, right? Every time, everywhere is freezing, and Texans they were suffering. And down here in Santa Monica, in Los Angeles, Southern California in general, we are so dry, and you see the crazy wind, right? It's blowing every day, and the air is so dry. My nose is was bleeding last week. So I keep drinking water and keep myself hydrated. So I hope you're doing the same. So why, right? Why in Texas they're so cold? And why in LA last week is so warm and so hot even? It's like unusually hot in Southern California, right? Why? Let's understand it, how our solar energy heat up our atmosphere and how the ground heat up the atmosphere. Actually, our ground is a more important source for our atmosphere. Okay. I thought the energy is just coming from the sun, but actually no. So let's figure it out by using this in this module. And this video, I want to introduce you my lecture presentation. Can also hopefully you will find it helpful when you read the textbook. Okay, so let me share the screen. All right, so I hope you see my screen, and this is lecture number 2, understand temperature. Okay. All right, let me present. Okay, so you're going to use our meteorology today, that book, and you're going to read chapter 2, these pages, and chapter 3, these pages. Okay, so this meteorology today can be downloaded from Canvas. You see that PDF, right? Okay, so this picture show you the nighttime temperature and the daytime temperature. You see, in one day, we actually don't have, the constant temperature, right? It's constantly changing. And that is why when you do the weather log, it's very important to average them out. Okay, so yeah, you know this. Okay, so this is outline. Outline first, we are going to understand energy. Most importantly, we are going to understand radiation energy. Okay, the waves, the radioactive waves, and its transfer in atmosphere. Okay, and the second one is heat and temperature. So when the energy get into atmosphere and our ground, how it turn into heat energy. Heat and radiation, they're different. They're different. And then eventually will raise up your temperature or cool down your temperature. And temperature and heat also two different concepts. Oh my gosh. So let's understand them. Okay. And eventually we are going to understand the Earth and atmosphere balance. Okay, energy balance. So, well, Earth, 40 million years old, right? Billion, sorry. Well, very old. Earth is 4 billion years old, okay? And uh, our energy balance is maintained without human being. So how we are going to understand how the solar energy pass the atmosphere, get to the ground, heat up the ground, and ground heat up the atmosphere in turn, and then how this process, balance out. Okay, the incoming energy and the outgoing energy. Okay. And lastly, we're going to understand the daily and seasonal variations of your temperature, of our temperature. Okay. So in this week, week 3, you're going to read the pages about those chapters, about those topics, and to summarize. Okay, and next week our discussion is application. Apply what you learned to understand the daily and seasonal variation temperature of one place. Okay, so that's next week. All right, so make sure you can answer all these questions in each bullet point in your summary as well. Okay, and for the sake of the quiz. All right, so radiation energy. Radiation energy, well, is actually is a wave. In fact, actually, all the items, all the matter, okay, you and me actually can emit this type of energy. We call it electromagnetic radiation energy. Okay, why it's so complicated? This name, because this actually is caused by photons, the movement of the photons. It's a little bit complicated, but you just think about this wave. Actually, it's not just one wave, actually, two waves. One is in a magnetic field, like this blue arrow indicates, and the other one is electric field. And those two fields actually perpendicular to each other. Okay, and you will have this red wave, it's like an ocean wave, and you will have another wave, it's like a snake, horizontal, and they perpendicular to each other. So this single radiation wave or radiation energy contains two types of waves, basically electric and magnetic. Okay, but most importantly, we measure radiation energy by using wavelengths, this variable. Okay, so what is a wavelength? Wavelength is the distance between one peak to the next peak, or one valley, one trough to the other trough. Okay, to the next trough. So that is a wavelength, and you can see different type of radiation energy actually have different wavelengths. That is how we differentiate them. Okay, so you can see, for example, our visible light is one type of radiation energy, and in the visible light, you have different colors, you have different wavelengths. So you can see these are the wavelengths. Okay, so obviously red has longer wavelengths than violet. So why it matters, right? Because the smaller the wavelength is, the more intense the energy this type of radiation wave carry. Okay, so it kind of like the purple light, they travel very fast. Okay, they're in a rush. They move very fast. They carry a lot of energy. Okay, well, more intense radiation energy you can see here is the gamma rays, UV. Okay, we use that to gamma. You use gamma rays to cure cancer, right? And cosmic rays. It's very it's harmful to our human body. So last week when we were landing on Mars, if astronauts they need to wear special suits, right? Because those very intense energy may hurt them. Okay, they hurt them. So yeah, but the longer wavelengths, like your red or ultra wide, I'm sorry, the longer radio waves, actually they're not harmful because their energy is not intense. For example, I love NPR, you know that, and the radio waves. Well, in my house, everywhere we have those radio waves, including my phone, including my computer, including myself. Actually, any objects, as long as its temperature is greater than this temperature, this many Celsius or this many Fahrenheit, you can emit radiation energy. Okay, so my body temperature about like 90, 98 Fahrenheit or 36.5 Celsius. I know Celsius better. So yeah, so I emit radiation energy. But the thing is, my wavelength is very, very long. You cannot see it with our human eye. Just see those visible light because our eye are just only sensitive to those visible light. Okay, but long story short, this is your radiation waves. Okay, they're not heat. They're not heat. Okay. So speaking of the radiation energy, well, in this chapter, we are more concerned about sun's radiation energy and Earth's radiation energy because Earth's surface, the temperature, of course, is higher than that absolute zero, right? Okay, so but the thing is, the sun is much hotter than the ground. So this is a very, very important difference. Because the sun is hot, it carries more energy. Okay, so we call the solar energy is short wavelengths radiation energy, but the Earth is longer. Okay, it's longer wavelengths. That is a very important thing. That's the key to understand our heat energy, temperature, and also why we have that greenhouse effect in our atmosphere. Okay, so here. All right, so when the solar radiation coming down pass through the atmosphere, this is a very important thing to keep in mind. Our atmosphere actually can absorb a lot energy from the sun. To be honest, in fact, not to be honest, in fact, only half, actually a little bit less than half, about the solar energy can get to the ground, can make it to the ground. Okay. Last week, you have a classmate, Candice. She asked me this question, Professor. UV, we can use UV to break down, because the energy is very intense, can break down a lot of, molecules, for example, ozone, right? You have ozone depletion. But why UV cannot break apart our water on our ground? Why we still have water here? That's such a great question, right? Because 99.9% of the UV has been absorbed by ozone in stratosphere already. Very, very little can get to the ground. So that's why our water is lucky. We are lucky. Otherwise, no life on Earth. Okay. So, well, UV carry a lot of energy, so that's why you can see those high intense solar energy actually get absorbed. Only, okay, your visible light can pass through. So in our atmosphere, we don't have corresponding gases or molecules that can absorb visible light, so they can get to the ground. This part is the major solar energy source. Get to the ground, heat up the ground, okay, light up our environment. Okay, so it's a sunny day in LA today. All right, so yeah, visible light can get to the ground, but when you move to the longer wavelengths, so we can see we're moving to the longer wavelengths, the absorption rate of our atmosphere to those radiation energy actually become a little bit complicated, right? Certain wavelengths you can absorb a lot, but here you can see these wavelengths from like I would say 20 micrometers, negative to the power of -9 micrometers, to about like 2 or 4 millimeter. This range, you can see, that is infrared. That is the radiation energy our Earth, our ground can emit. Okay, so that's why here you can see it's right here. So you can see those energy will be absorbed 100%. Okay, that is from our Earth. So in other words, the sun, the energy can come in through the atmosphere, right? So they cannot be used. They cannot be used to heat up the atmosphere, right? It pass through. Nothing get absorbed. And in turn, the Earth's energy actually cannot get out. So it will be absorbed. right? Okay, and then this part of the energy is a major energy source for our atmosphere. So, see, that is the key to understand greenhouse effect. This is the thing. Okay, this is the thing. The sun can pass through the atmosphere just like the sun can pass through the window of your car, but the energy inside your car, inside our or in under in our troposphere cannot get out, right? So you will become warmer and warmer. But our atmosphere itself can also emit out a lot of energy back to the ground and also to our space. So that is balance. Is balance. Okay. So I hope I make this part clear because it's very important. So you can see. Let me annotate. Okay, let me put my mark down. And you can see here. This is the solar energy. Solar energy through. Okay, so this is the solar energy can pass through. Let me go here. Okay, but color, let me annotate. It's right here. Okay, but our Earth's energy is absorbed. Okay, so yeah, so Earth's energy is right here, and solar energy is right here. Okay, so key to understand greenhouse effect and energy balance. Okay, all right. Okay, then our the sun, let's go back to the sun. Okay, when the sun, the solar energy, those waves pass through atmosphere, those waves will also be reflected and scattered. So what is reflection? Reflection is the mirror. Okay, the sun rays heat those particles in our atmosphere, especially those liquid and solid particles. Okay, so they will be bounced back. We call that reflection. Okay, what is scattering? Scattering is a little bit more than reflection because it's your outgoing waves can go to all the directions. That is scattering. Scattering for our atmosphere is very interesting. Our atmosphere molecules, those gas molecules and the liquid droplet and solid particles, we call them aerosols. Um, they are very good at reflecting blue and purple, those visible light rays. So that is why our sky is blue. Our sky is blue. Okay, and there's a very important thing to measure how much energy get reflected or scattered back to the space. Okay, back to the space. So that is called albedo. Albedo. Okay, different type of the surface have different albedo. So you can see snow is more, you can reflect more, right? Because that's why when you go out for skiing or high up the higher mountains, you see snow, you need to wear glasses, right, to protect your eyes because the reflection is very strong. Okay, but compared to asphalt or those vegetation here, they have relatively low albedo. It means more energy will be absorbed instead of reflecting back to the space. Okay? And well, the greenhouse effect. I introduced you this already with that absorption slide. Okay, so you can see the shortwave solar energy can pass through our atmosphere because no molecules can absorb them. Okay, they won't be used to heat up the atmosphere, but long wave Earth's energy, radiation energy, cannot get out. We have that almost 100% absorption here. Okay, so you can see, well, those energy will be absorbed by atmosphere. That is a major energy source for our atmosphere. Okay, so if we absorb more, our temperature will get higher, right? Okay, so that is the greenhouse effect. actually we have this natural greenhouse effect. So in the past, without human being, we don't have higher and higher energy. Even our atmosphere keep absorbing the energy from the earth, right? Because atmosphere in turn also give up the energy to the ground and also to the space. Okay, so this incoming energy, let me annotate. Okay, this incoming energy to atmosphere and outgoing energy from atmosphere, you draw more arrow, okay, and to the space, they balance out, okay? But our greenhouse gases, they contribute this part, okay, because now our human being help emit more and more greenhouse gases in our atmosphere. They can absorb more, but they give up less. So that is why there's more and more energy, okay, radiation energy capped or is capped in our atmosphere. So that's why we have that soaring temperature. So this effect, we call it enhanced greenhouse effect. Okay, so that is a very important concept for this chapter. Okay, I hope I make it clear to you. All right, so then what is heat? Heat energy is different from radiation energy. Radiation energy, you know, is waves, right? But heat energy is we call that moving energy, okay? That measure, okay, that is how fast those molecules, they vibrate like this. Okay, so energy causes the atoms and molecules always in motion, and this motion is heat energy. Okay, so basically they're the same. When you have those waves, radiation waves, they will excite the molecules, the atoms and molecules in our atmosphere to make it move faster. Okay, and this wave, this radiation type of energy will be transformed into those vibrations. That is speed, right? The higher the vibrating speed is, the higher heat you have. Okay, so that's a different type of energy, heat energy. We call that the kinetic energy, means moving energy. Okay, so you can see there's several things we need to know. With heat energy, we also call that thermal energy. Okay, and when you put well, hot things and cold things together, this energy transfer, we call that contaction. You know, it always transferred from warmer object to cold object. Okay? So key difference here, heat energy is the vibrating energy, is energy in motion, but radiation energy is waves. Okay, we can use waves to make your object, the molecules and atoms move faster. That is how you transform your your radiation energy to heat energy. Okay. All right. So then, what is temperature? Temperature actually is the measurement how fast our molecules move. Okay. If your molecules vibrating fast, okay, the speed is fast, then you will have, you know, different higher temperature. Okay, and heat and temperature are related to each other but different concepts. I hope you can click on this link and also read your textbook to see the difference. Okay, so in general, temperature is a speed, is a measurement of your speed, the speed how fast those molecules vibrate. Okay, all right, so then what is specific heat capacity? Right? So, well, when the radiation waves hit up the molecules, some molecules they're lazy. They don't want to be. They are very hard to excite them. Okay, but some molecules is relatively easier, right? Okay, so that is lead us to this concept called specific heat capacity. So water actually can absorb a lot of radiation energy without being excited more a lot. Okay, so that means it's very hard, very difficult to heat up water. So for example, later I'm going to boiling my pasta, okay, for lunch. Well, it take water like 5 minutes to, 5 minutes to boiling, right? But my pan, the aluminum or cast iron, the pan can be heated up very, very fast, right? Okay, the same energy from my stovetop, but it takes longer for water to be heated up and also cool down if you turn off the heat. Well, the aluminum, okay, or other metal, okay, they will become cold like after like 1 minute, okay, or second, right? Okay, our water, it's very hard for water to lose the energy. So that is why in summer we all want to go to the beach, because even with the same amount of solar energy shining down, we actually have different temperature in the water and on land, right? So that is the specific heat, this concept. Okay, so let me move around this solar energy, make my face look a little bit. I have stripes on my face. Okay, anyhow. Okay. All right. So, well, this is the phase change and water of the latent heat. So, as I said, the solar energy can be used to speed up our molecules movement, but can also be used to change the phase of water. Okay, what is the phase of the water? That is, liquid, solid, and gas. Right? What's the difference? That's the distance between different water molecules. Okay, so those wavelengths, even they cannot, break apart our water molecule, the hydrogen and oxygen, these atoms, because they have this very strong uh, hydrogen bond over here. Okay, no, I'm sorry, that is a bond between your hydrogen molecule and your oxygen molecule. Okay, it cannot break this one, but they can break this hydrogen bond. Okay, if you have more energy, even other type of energy, okay, from stovetop, your heat energy can break them apart. Okay, this is break it apart, and if you change the distance, change the hydrogen bond, you will change the phase. Okay, but here the thing, you can see from solid ice, your water molecules organize this like this. They hook up very tightly. Okay, so those energy is used to break them apart. So that is why when you melt your ice, you actually absorb energy. Okay, and then when you turn your liquid water to vapor to gas water, right, you break them, you push them apart even further. So that is why when you see the water boiling or evaporation, you need energy. But opposite, okay, condensation, when the gas water become liquid water or liquid water becomes solid ice, you release energy. Okay, that's why your freezer, they need electricity to take away those released energy, right? When you freeze your water. Okay, so that is the latent heat. It's not. Oh, what's going on here? Interesting. I see this uh, mouse here. Okay, that's great. Oh, I see the pointer. Okay, from a Google slide. Okay. Okay. Anyways, so here you can see this is the different phase change, and your energy is not used to speed up, or yeah, it's not to speed up or keep the speed of your molecules. So this type of energy, you won't see temperature change, right? You won't see temperature change because those energy is not used to change the speed of your molecules. It's used to keep apart your water molecules, right? So you won't see temperature change. We call that latent heat. Latent heat. Okay. All right. Then heat transfer in atmosphere. I introduced you this already when we talk about the greenhouse effect. But here is the thing what happened on the ground. Okay. So you can see solar energy shining down to the ground. Most of the solar energy will pass through right? And the ground will be heated up. Those solar energy can be absorbed by our ground, and our ground temperature will be raised up. Ground get warmer through one thing, direct contaction. Okay, through direct contact, our ground can heat up the air. So this is called conduction. Okay, and when this layer of air that directly contact with our ground get heated up, they become warmer. Warmer air, like your hot air balloon, right? They will be rising because hot air lasts dense. Hot air lasts dense. So they will be rising up, and cold air, they are heavy. They're dense, so they will coming down. So you can see in our troposphere, you constantly have this. We call that convection. Basically, warm air rises, cold air sinks. So that is why our troposphere, you have this mixing happening. Okay, they take the energy they get from the ground all the way to the tropopause and then coming down. Okay, and this rising air, when the air is rising up, it gets cooler and cooler, you will see condensation. Then that is a cloud, that is the rain, that is your snow, that different weather events we are going to study later, okay, in the following modules. Okay, so this is a way to mix up the energy they get from the ground. We call that convection. Convection. But here, don't forget, you also have latent heat here, okay, because those water can absorb the energy from the ground, right? And then, well, also energy from the sun, those water, right? Okay, they will be transformed into gas phase, evaporation, right? And then those gas water will rise up through this rising, carried by this rising warm air to the atmosphere, and then condense out to liquid water and then release the energy to atmosphere. See, this is latent heat. So latent heat is also very important for its energy source from the ground for our atmosphere to be heated up. This energy is from the ground. Okay. All right. So that is why here we have in your textbook we have this balance. Okay. So you can see. Let me walk you through one more time. You have solar energy coming down. Some of them get absorbed by our atmosphere, like ozone, right? Like other gases can absorb part of the solar energy, okay? And some of them can reflect by our atmosphere already. And some of them can also be reflected by our ground. So you can see eventually only 51% of the solar energy can make it to the ground, okay? And make it to ground, and the ground will absorb this part of energy to be heated up. Okay, and when the ground heated up, I want to bring your attention to this part. So you can see infrared energy, they can radiate a lot energy to our atmosphere, and atmosphere will mainly absorb this part of the energy. Okay, and our atmosphere in turn reflect back this much of infrared energy to the ground, okay, and also to the universe. So those numbers they balance out, okay, the incoming energy to the atmosphere and outgoing energy to atmosphere, okay. And oh, don't forget another very important source from the ground to atmosphere is this latent heat. Okay, they will be carried by this uh, convection, the rising air to our atmosphere. Okay, and also this mixing also can carry the energy up, the heat energy up. Okay, so this is the Earth's atmosphere energy balance. Right? Okay, so but this balance, the picture you see before on the previous slide is global average, but not everywhere we have this balance, right? In close to the tropical area like Singapore, like Philippines, right? You have more incoming energy because their sun is stronger. Okay, compared to Alaska, their sun is weaker. But globally, we have this energy balance because our ocean, our atmosphere, their emotion, they keep constantly moving. They can carry the surplus energy from the tropical region to higher latitude to balance out the deficit there, okay, to transfer extra energy. A good example, our Gulf Stream, okay, from the Gulf of Mexico, Florida, Louisiana, that part, and then go all the way to the Europe, right? Okay, they can transfer the energy all the way to Europe. That is why in UK, in the Netherlands, right? They can still maintain a very good temperature up there. Okay, Finland, right? It's not freezing cold. Okay, all right. So let's see. Yeah, okay. So the daily warming and cooling our atmosphere near the surface, that is very, become very easy to understand, even you understand this heat transfer, okay? Solar radiation shining down, absorbed by our ground, and our ground, will release the longer wavelength energy to our atmosphere, and atmosphere will absorb this part of energy to get warmed up. Okay, and during the nighttime, okay, you don't have this. Let me go. Let's just use this one. You don't have this radiation. Our ground will be cooling down, and our atmosphere will in turn heat up the ground. They have this exchange, right? So that is the basic concepts, okay, to understand the warming and cooling air near the surface. Okay, convection and convection. Okay. So, well, then in meteorology, okay, we have this, energy curve. Okay, so wind can actually help us to even out, to mix those different temperature, okay, at lower level and upper level. So you can see if in the afternoon the wind is calm, you don't have wind. Well, you can see here this temperature, right? Okay, and this altitude. Well, you can see at the ground level, very low latitude, very low altitude, you have very high temperature, but this temperature will fast decrease. Okay, you go this side, decrease when you go up, when you go up. But windy afternoon, you can see, well, that will cool down your surface temperature, but can also carry those temperature to the upper atmosphere, right? Okay, so here, well, in the evening, the same thing. Okay, you can see this is the air temperature. Okay, because our ground specific heat capacity, okay, give up the energy very fast, but air relatively give up the energy slowly. Okay, so usually in the night, okay, without the sun, our ground the temperature will be lower than the atmosphere. Okay, than the atmosphere. So you have cold air actually at the ground. Okay? This bring us the let's see. This bring us the energy, the concept we learned in the last week, last module. That is energy inversion. Right? You have cold air at the ground. All right. Okay. Okay. So this is the daily warming and cooling of the air near the surface. Okay. All right, so this is the study of the temperature curve. Let's see what I'm going to emphasize here. Oh, when you get a higher temperature, okay? Because again, it's not at the noon you have the higher temperature. It's later afternoon. Well, because ground is a more important energy source. Okay, they take time to heat. It take time to heat up the ground and also in turn heat up the atmosphere. Okay. All right, the seasons. Okay, so what else has seasons? I want you to read this textbook and our video on the study guide. You have very good video to introduce you this. Basically, distance to the sun is not the answer. The tilt of the Earth's axis is the answer. Okay, so you can see our Earth is always tilted this way. Okay, when it's orbiting around the sun. Okay, so you can see in January we are on this side. Well, we are in winter in northern hemisphere because our side, the North Pole, is tilted away from the sun. You have less solar energy. Okay, but in July, your North Pole tilt towards the sun. Remember, you need to keep this direction. Okay, so we are more leaning towards the sun. So we have energy. So that is why in the summer we have hotter temperature. That's it. That's it. Okay, but yeah. So let's see. Yeah, this angle, the angle when your sun at your location. Okay, when the sun hit the ground, this the ground, this the sun. This is this angle between your incoming solar energy and the ground. This angle, we call them solar altitude. So obviously, the solar altitude at different latitude, they're different. Okay, Earth at the equator, you have like 90-degree, for example. But if you go to the higher latitude, like Alaska, you have more oblique energy, right? Tilted energy, just coming from the ground. So you have less intense energy. So that can also affect your temperature. Okay, so yeah, read that chapter and also watch our videos that become more clear. Okay, because here I cannot make it in animation. I think that video will help a lot. Okay, yeah, so here you can see this is your solar angle. Okay, in this case, you have more intense energy. In northern hemisphere, it's in June. Okay, because you shoot the solar rays hit the ground in a more higher and a larger angle, and those energy is more intense, just like you use a flashlight. You shoot the light rays to people's eyes. It's very intense, right? People cannot open the eyes, but if you tilt it a little bit, this intensity will become weaker. So if you have this solar angle a little bit smaller, you have less intense solar energy, then the temperature will become lower, right? Yes. And also different day lengths. We have daylight saving time, right? Change. So in the summer, because our daylight is longer, okay, when you go to the upper higher latitude in North Pole or South Pole, you could have like 24 hours day, right? So if you expose to the solar energy with longer time, for longer time, you will have more energy, right? That is, yeah, that's another factor. So day length and solar altitude. Okay, so yeah, so this is just another concept of the where you see 90-degree sun. So you can see this guy, his shadow is just beneath his feet, right? So this the solar energy coming from the sun. Okay, 90-degree hit the ground. So where you can see it, just between those two latitudes. Okay, 90-degree, I'm sorry, 23.5 degree north and south, that tropical region. Okay, and on different days. So this is your calendar. This is your calendar. Okay, and this is the calendar for all the days in a year. You can look it up. So for example, today is March the 1st. So you can see here, March the 1st should be here. So today our 90-degree sun, this is the equator. So 90-degree sun, let's see, it's about 7, I would say, 7 degree. Oh, 9. Here, let's go here to this direction. 8 or 7 degree south, right? Okay, so that is where you can look it up. Okay, find your date, then go to the side. Okay, all right, we call that Alanema, by the way. And the rest of the slide, I just want to show you on different important days, solstices and equinox, how the sun heat up the earth. Okay, so you can see in June, so on June solstice, where you have the most intense energy, northern hemisphere, 23.5 degree north, because the solar energy here, the solar altitude is 90 degree. Okay, you have a relatively longer days. Okay, and in terms of day length, North Pole, you have 24-hour day length. Okay, when you go to the higher latitude, you have longer and longer day. So that's why in general, in June, in summer, northern hemisphere is warmer. It's in summer, right? And southern hemisphere is opposite. Okay, and December solstice totally flipped. Okay, you can see southern hemisphere have South Pole have 24-hour day length, and the most intense solar energy is at the 23.5 degrees south. Okay, so yeah, so this is how the season affect our temperature. Okay, March or September equinox. Very importantly, that is everywhere, all the latitudes. We all have 12-hour day lengths. Okay, the only difference is solar altitude. So this 90-degree sun is at equator. Okay, and then we'll go to the higher latitude. You have less and less solar altitude. Less intense solar energy. Okay, so that is the thing. Okay, so you can see this is our seasonal change at different latitude. At equator, basically, let's use this beautiful chart. You don't see that color change, right? Means our solar energy doesn't change that much because your solar altitude doesn't change that much, and also your day length doesn't change that much. But when you go to the upper latitude, your solar energy actually change a lot because go to the North Pole or South Pole in the winter, for example, here Northern Hemisphere winter, you could have zero solar energy because day length is zero. Okay, so they fluctuate a lot. We call that stronger seasonal cycle. Okay. All right, so this is just how the sun, uh, above the ground where they are, okay, to show you different location. Okay, so you can see, let's go to the North Pole. North Pole, you have this, the constantly just, on the horizon. Okay, in the summer, it can go this up. Okay, but let's compare to equator, right? Okay, equator, obviously, constantly you have this higher solar altitude. Okay, solar altitude and very even day lengths. So you don't see that change that much. Okay. All right. So I think that's it. I hope this video is a little bit long, but I hope it's helpful to help you read the textbook and make sure you can understand. You can answer all these questions before taking the quiz. Okay. All right. Okay. Wish you a happy and productive week. And I will see you during office hour and also through emails and messages. Okay, bye for now. Happy Monday. Happy week 3.